case studies in directed energy deposition. This is sort of one of a two-part lecture. The next one will deal with hybrid DED processes and with welding. I'm sorry, repair. With repair. So let's just jump right in. I thought I would. We okay? Once listening, you've had a nice opportunity to look at this slide. What I have is a list for you from last year of all of the known directed energy deposition companies in the world. So we start with Europe, and you can see that there's maybe 15 companies. There's some very large ones, as like that are very well known, and some others that perhaps are not so well known. Also, I list here a number of features, so you can see the beam. Well, of course, there's the country, and then the beam, whether it's plasma arc or laser, electric arc, or a plasma arc or electron. So those are all listed as well as whether the company uses powder or wire or both. And then there's, I also made a note, sort of in anticipation of the next lecture tomorrow morning, Friday morning. I list the manufacturers that produce hybrid or multiple material machines as well, fabricators. And then there's a few remarks here. So yeah, this is Europe. This shows the list for North America. And certainly there are likewise there's some old established companies like Automotive and Ziaki, and then some other ones that perhaps are not so well known. And again, we can see the same kind of information. So I think hopefully in the printed material you have, it will be readable and you can refer to that. Here's the third list, the third of the tables on Asia. And here's the one I noted. There's one Indian company. It was a Marat Prince Renner. It doesn't sound very Indian to me. It sounds German. So maybe, I don't know, maybe it's a German company that's in India. I'm not sure. But it's producing directed energy deposition. That company is laser with powder and wire. But certainly, Japan has a few, China and Australia as well. And I'm not completely sure how Brazil wound up in Asia, but at the very bottom of the list here. But at any rate, I assume that should probably belong to the Americas. So anyway, so altogether, maybe 40 or 50 DED companies in the world that are producing machines that are being distributed for a variety of a variety of applications. I wanted to talk some about ASTM F3187. It's a very fine document. It's called a guide. Standards can produce or have a number of purposes, but one of the purposes is just to sort of give good advice based from the experts on how to do something. And that's what guides are. And so this is simply advice from the experts. It's not a requirement. We wouldn't necessarily say, we conform to this standard. It's just simply good advice on things maybe you might consider in an effort to do good practice with directed energy deposition of metals. And so I'm not going to go through the standard in great detail, but I did want to read through this because this says basically what's in the standard so that you know. And there are these various chapters, and I've highlighted them in red. So there's a section on a high-level description of the features and benefits of DED, makes some comparisons between DED and other metal 3D printing technologies. There's a section that describes the machines used to perform DED, and so basically like the introduction we did here this week. Their atmosphere control is another important area, and so there's a separate section dealing with that. And also there's the feedback used for DED, particularly for metal powder or metal wire. So the features of each of these are discussed, and the importance, the proper cleanliness, safety, and some advice on how to make that happen is also included. Then they talk about the DED process itself, how to define, measure, control the key parameters. There's the setup, calibration, and maintenance issues for DED, followed by post-processing of DED metal parts, and inspection, heat treatment, finishing processes for DED. And there's also a section then on safety and the safety concerns. This is very important in additive manufacturing. And so it talks about those. It talks about how to put together a manufacturing plan that would be used to implement DED in a production setting. And so this, again, for commercial use is very important. And then finally, there's a section on how to specify the process. So it talks about basically how to communicate between suppliers, buyers, users of DED technology, so to make sure that everyone's on the same page. So it's a very nice comprehensive standard that that has really sort of covers the entire waterfront of DED. Yeah, it's ASTM F3187. This is kind of a nice, I thought this was a nice graphic that shows sort of the placement of directed energy deposition and what some of the key features are. This comes from the ASM Material Handbook, slide 24A, the second of the two standard texts on additive manufacturing. What you see is it shows basically this trade-off between build deposition rate, how fast we can deposit material, and the feature resolution. Because the two typically are opposite to each other. I can dump a lot of material quickly, but typically the resolution is not very good. Or I can build very slowly and have nice features. And this is, to be honest with you, I think this is something that probably plays across a number of manufacturing technologies, not just additive. But what we see here is that we can go from, if we start with the highest feature resolution over here and the lowest build speed, where what we find basically are the powder bed fusion technologies, but right very close is laser powder DED. So it produces, you know, good detailed parts, but with relatively low build speeds. And then following that comes the laser wire DED, which again has we can go faster, but without as much detail. Then comes arc wire, comes next, and then finally the electron beam for the especially wired electron beam, which builds at fairly high rates, but without much feature resolution. And then finally they have some of the really the only ones that produce metal deposited more quickly are the cold spray technologies. We didn't really talk about that very much. This is I think friction stir process if I remember correctly. So yes, in terms of sort of, you know, if you want to think about the criteria of which of the various DED processes you might consider using, you know, laser versus electric arc versus electron beam, and powder versus wire. This, at least for two considerations, gives some rationale about what you might consider selecting. This also shows the application space for metal AM, and what's shown here is it's sort of a similar kind of plot. It shows the accuracy of the part, and in terms of, say, a tolerance versus the surface roughness. So what we have is down here at the bottom are highly accurate, very smooth parts, and we see like polishing down here or machining processes. And then up here at the very top are parts that are not very accurate and with high roughness. And of course, you know, it's not surprising that wire DED, which is really not, you know, it's not really designed for surface finish or tolerance. It's designed to deposit material very quickly in an edge shape. And so we find that up here at the top, along with the powder DED that comes in on the hills as well. And then the other metal additive manufacturing processes are all up here in the same region. So it shows again where, you know, kind of where DED fits in. There's these sort of web plots that show. It's a good way to sort of from a selection perspective to show what's important in a graphical kind of way. And so if you haven't seen this before, there are a number of criteria here: the build rate, the complexity, the accuracy, the cost savings going on around material utilization, mechanical properties, post-processing requirements, and the platform flexibility, the part size. And what we have is we have these shapes here that are for different manufacturing processes. So the one that's sort of the solid blue line here is for WAM, that's the wire arc additive manufacturing process. So it's not surprising that, for example, in terms of, let's see, something like build rate, you know, that's fairly high, you know, good, you know, relatively cheap, good you know, mechanicals and other aspects there. So yeah, it shows how this works. Powder bed fusion is the dotted line, which let's see if I can find out. Maybe it's this one right here. No, it's here. It is here. This one is the dotted line. So this is powder bed fusion, and so it, you know, it tends to really shine with complexity and accuracy. But in terms of, say, build rate, you know, not so good. And it seems to be fairly, where's the weak point? The cost savings is fairly weak, right? So okay, so this plot, so it's kind of helpful for, again, for sort of doing the process selection. The wire bed, I guess This is, I guess, yeah, I guess this is the wiper that we see, and so we have this outline as well, showing that build rate's very good, materials utilization, mechanical properties are good, accuracy and complexity maybe not so good. So, okay, so moving on now after that introduction to some case studies. What I show here, I just sort of gleaned from the web. Basically some basic examples where DED tends to shine, and you can see that they fall into these areas. Exhaust ducts, piping, ducting, nozzles, manifolds, structural frameworks, cases with flanges and bosses. We've seen a number of those. Combustion components, airfoils, vane packs, inlets, heat shields, long internal channels, weldments on piping, near-dead shape forging replacement, and gradients in multiple materials. Basically, it's sort of the places where we see the DED being used. And again, these are application areas where we can really take the best advantage of the strengths of DED. So let's look at some of these. I'll just go this way. Oh, no, maybe I can't. There we go. Okay, so maybe I'm back now. Yeah. So here's the first case study. It's the material is 304 stainless steel. It's a fairly large dimension, about 0.8 of a meter on the long dimension, and 700 millimeters, 0.7 of a meter across, and 0.36, about a third of a meter deep. So this is a very large part. Again, it takes good advantage of the rapid build rate, which is one of the long suits of DED. It was built with wire arc additive manufacturing. It was a BLT machine. And the technical description of this from the website is, the cam has a complex structure and contains a large number of suspended structures. The traditional method is difficult and time-consuming. So here we can build this part with DED. And the features are not highly accurate, but there are features that are important to maintain, and directed energy deposition is able to comply with those. So that works well. So again, this is sort of the category of high material deposition rate, large part. Here's another one. This is a case study of that shows aluminum. It's aluminum 6 mag alloy. It's a excuse me. So it's this part that's built and then finished machine. Again, it's a large part, 1.4 meters high, and with I guess it's 1.4 meters high. It says the diameter is over a meter as well, so I'm not sure how that figures in. But at any rate, this description is the overall structure of the cylinder is conical with upper and lower flanges. It's traditionally assembled by welding and splicing, which has a long manufacturing cycle and high cost. So the fact that there's a little bit of shape complexity tends to lean the part towards an additive technology, and because of its size, it just makes sense to use DED. Here's some channel wall nozzles are shown here. They're nozzles with liquid cooling channels, fabricated with very thin walls, so it's a 1 millimeter wall on these. They do it with nickel and iron-based alloys. It's clear here and here. I'm not totally sure. Maybe it's over here on this third one. Shows it in service. So they fire tested it in cycle testing. So I assume this hot item over here is the channel wall nozzle. Again, it's a good example of directed energy deposition. Dual wall ducts, again, we see the part here. You know, the dimensions is nominally 150 millimeters. It's a continuous dual wall, so there's, I guess, 2 walls here on the part, and with a 1.5 millimeter wall thickness. So again, it's a part that's reasonable to produce with directed energy deposition. And the geometry clearly is one that really speaks for additive manufacturing. This shows a case for the for 718, the nickel-based alloy. It's I think we may have seen this one before, but it shows the build of this part. But basically, this machine, I guess it's an RPM Innovations machine. What they have is that they have multiple degrees of freedom on this, so it's a multi-axis fabrication. So what you see here is building the main body of the part. Here's the final part over here. But what they can do is, intermediate is they can actually, this actually shows them rotating the platform relative to the energy source so that they can actually go in and produce these other bosses and these other features without, in a way that really minimizes the amount of waste of material. So it's a very nice part here that can be produced, and it's enabled again by the multi-axis nature of the process. This shows again a relatively large part. It's a freeform tie 6/4 part that's been built, and it's I'm not sure what it is, but it's a fairly long, slender, ribbon-like structure that again it's 2.1 meters tall, so it's quite tall. Took about 2 weeks to build. 2.3 millimeter thick ribbons that were used to construct this. So again, this is something it's fairly complex in terms of the arrangement here, and it's a large size. So so we have the sort of the requisites in place for DED. All right, this shows an example of multiple materials, the gradients that can be produced. This is it's Inconel 718, Inconel 625, and a Haynes alloy. And what we see on this side over here is it's difficult to see the layers, but basically they started at the bottom with Inconel 625. Transitioned over a small area to gradiate from the 625 up to Haynes 230. Then they ran Haynes 230. Then there was another gradient in the build where they were mixing the Haynes and Inconel 718. And then finally at the very top, they transitioned to the third alloy, 718, in the build. And so they show some plates that have been built this way. And so they have the transitions. Presumably, there's a motivation or a reason to do this that drives the process. And again, one of the strengths of directed energy deposition is the fact that it's relatively easy to produce to generate material gradients because we can use at least with powder, multiple nozzles, or require multiple wire feeds. Okay. The next one I have to show is another 718. This is a combustion case, so it's for part of an engine application. And we see, so we can see in this case it's fully deposited 718 case. The ODE and the flange are machined post-deposition, so you can see that over here on the final part. and the bosses were added, which I guess are these features down here, to pre-machine, the pre-machine on the surface. So you basically build a part, and then machine it out, and then add the bosses and finish those up. So the ID final was final machined after the deposition of the bosses. So here we see the final part, which is, again, it's a very nice application for the directed energy deposition. Here's another one. And this is from a different company. It's a so-called yaw damper bracket. I'm not sure what that is. He said it says that it ensures vehicle stability on high-speed trains. So I think that's fairly important device or part. This shows the final product over here. This shows sort of a schematic of the build plan for the part through directed energy deposition. And I'm supposing that this is shows the parts that Grabs has built sitting on the platform. So this again is a wire additive manufactured, wire arc based additive. And so again, their point is that it makes it possible to adapt the component at short notice during the printing process, depending on requirements. So, and I'm not sure what the requirements are, but apparently they can vary from application to application. And so by doing it with additive, it becomes relatively easy to change the part on really almost on the fly, and to build a part that has the proper accommodations. So, okay. This is one that shows it's a Siemens part that is a load collar. Again, I'm not sure what these applications are, but it's heavy-duty gas turbine load collar located in critical downstream areas. So again, this is the part. This shows the part after the build, on the base plate. And this, I guess, shows again, this parking schematic of the thing. And it says, the production process can be improved, and 80% of the material can be saved. So in this case, we're going with a significant cost savings in terms of material utilization by using directed energy deposition instead of a traditional processing. I can imagine that this part, if this part were machined, there would be perhaps 70 or 80% material loss, and that's not the case here with the additive manufacturing, of course. And again, it looks like this was finished up probably not by machining, but maybe perhaps by green blasting or even possibly hand polishing, just based on the shape of the look of the part. So again, we have this is again, we're starting to see sort of similar, the similar structured designs. In this case, we have the case study shows sort of the design of this. It's a bell-mouth intake. It says delivery times and material costs are significantly reduced, so they can turn it around faster. Classic advantage of additive manufacturing, and the material cost. It doesn't say what the material is, but I assume it would be one of the expensive materials that's used, maybe titanium or a nickel-based alloy. And this shows the part as built and the part after being finished. So again, it's kind of a classic advantage for using additive manufacturing and certainly DED. This shows this is sort of the last of the parts that sort of have this shape. It's a gearbox housing and produced again by wire arc additive manufacturing. In this case, I guess still by Preferred. It said they say for various reasons production by casting or milling is not economical. So 3D MEP offers advantages such as weight optimized production with steel, near-net shape production, and cost effectiveness from lot size 1. So again, these are all the standard, the standard reasons why we would like to use directed energy deposition to produce the part. And again, this has the same look of a multi-axis deposition, where when they are depositing material, these perhaps maybe be deposited after the main column was produced. And again, this shows the final part, the finished part. And you can see that, again, what is relatively common is it's only the critical surfaces that are machined to produce the necessary surface finish. And the rest of the part, those areas that are not so important, we don't deal with. So, okay, this is something that's sort of completely different. It's an MX3D part. They actually had a contract to build a bridge, a footbridge, in Amsterdam. And what's shown here, this shows the installation. It's across one of the canals, I guess, in Amsterdam. And here's I guess the place where it was built. I'm not going to try and pronounce that, but it's it's an interesting bridge. This shows the bridge section in the lab where they were actually putting the build. And you can see that this is a robot arm type DED process that was used to do this. It was produced in stainless steel and wire arc additive manufacturing. And again, you can see it's a very large structure, 12 meters long and 4.5 metric tons. So it's this is really an extremely large part produced with wire arc additive manufacturing. And this was one that in the world of additive manufacturing, it was sort of a big splash application of additive manufacturing and construction because I kept seeing this various places as just as I was scouring around through the literature. They had it shows here it was a two-year license. The bridge is as best I know performed admirably. Again, it was a footbridge, so there was so it wasn't really a lot of heavy equipment crossing it, but apparently it performed well. And then, but unfortunately, it's after 2 years they removed it, so it's no longer present to see. I think we'll do one or two more, then I think maybe take a break. So let's do one per case. Again, it's another large part application here. In this case, this is for space. That's a Parade 1 launch vehicle. It's a 5000 series aluminum alloy, which is, I forget what, I guess it's aluminum manganese, or it's either aluminum manganese or aluminum magnesium. One or the other, I can't remember the 5000 series. Again, but it was as a space application, arc welded DED, so again, relatively high deposition rate for this very large part. You can see the size of it from on the right side from the human being standing there. And again, it shows the part in the process of being built on the left, and I think the part at or near completion on the right. And so it shows, I guess these are two separate applications. So on the right one shows this NASA near-net shape liner, which has built in a different alloy, JBK75. I'm not sure what that system is, but again, it was produced by laser powder application, and it's still a large part, as you can see, and it's 2.4 meters in diameter, 2.8 meters tall. So again, it's an outstanding use of additive manufacturing, directed energy deposition in terms of being able to produce a part that has that meets the needs in a way that's as economical as one might expect. So it's a very these very large parts, again, space structures, and we see a lot of parts like this, large parts for space applications. So anyway, so I think with that, let's we're going to be going a while, so let's say maybe a 15-minute break. Here, let's hook up again, maybe at maybe 3:40, and then I'll finish up the slides that I have on case studies. We'll just take a break. So, thank you. Now, one seems to be working. The PowerPoint is working, and so we'll see how we can do here in the final part of this. So I think where we pick up is here. This again is a large part application where this is an aerospace component. It was done at KJN Aerospace Northrop, California company. Laser wire DED, 45 kilograms of material in this 2.4 meters long. So this is obviously an aircraft. It looks like a wing component to me, maybe a part of the wing frame. And we don't know what the material is, but it does give a demonstration on how we can use the wire arc. The laser wire approaches. This part that presumably maybe has maybe a little better surface geometric definition that we saw with those mostly cone-shaped pieces that were produced with the arc welding or the arc approach and the electron beams. So there are a number of space applications for a DED, and I would like to here's one of them. Shows a rocket thrust chamber assembly, which is shown here. This shows it's a duplex stainless steel part. So this shows the printed part before finishing, and then as is shown here, and this shows the final finished part where they've done all of the machining on it. And so for this one they show it here. This looks like it's being packaged and ready to ship. And so again, duplex stainless steel took about 20 hours to build. They were depositing at 4 pounds an hour, so about 2 kilograms an hour. This is a fairly hefty build rate for this item. And so they talk about it stands 42 inches tall, so a little over a meter in height, thickness 3 millimeters. So again, a good application space for DED. This is a spherical tank, as you can see. It's again wire laser DED, and 316 stainless, and a 30 kilogram weight. So it's quite a heavy part that was produced, and again, it does a fine job for what it is. Again, it sort of works with the advantages of DED. The large part, we can build it very quickly. The geometry is not super complex, but complex enough that we would think maybe not about using some other alternative technique to produce this large part. So this shows an aircraft bracket, again wired laser direct energy deposition. It's I-64 and I guess if I do the math right, 100 millimeters, so I guess it's what, a tenth of a meter, or so, 160 millimeters by 34. And so we see the part here. Well, this one obviously has been finished. This is clearly in the as-built condition. So, and again, to get reasonably complicated geometry here. This is an automotive application. An automotive suspension truss support. Wire arc additive manufacturing aluminum material, and they show the advantages of this optimized design we get, which is enabled by additive, improved functional performance, lower energy requirements, and improved material usage. So we have this part as well. It kind of has a bit of a topology optimized feel to it as I look at it here, and over here, the functional performance reminded me, if I can sort of go off topic to finish the point, we talked some about the environmental effects or sustainability effects and where additive can play a part. And my conclusion with the environmental advantages of additive is that they're really pretty hard to come by. Unfortunately, people will make arguments in the literature about additive. Well, we have very high material utilization rates, so it's not like we're machining a bunch of material and throwing it away. And that's important because the feedstock, it takes a certain amount of energy to produce the feedstock. So if I throw it away, then it's not environmentally friendly. It turns out, though, the papers that I've seen and some of my own work with the environmental aspects is that in terms of energy, that just the additive manufacturing process itself, really it's a hard sell to say that it's really energy saving. Or even if we include the feature slide, we're using a lot of material. We're being effective with the use of the material. It's still a hard sell. It's because we're dealing with things like lasers, which have a very low energy conversion. We're dealing in some cases with heated beds, which that have to stay hot for a very long build time, maybe 30, 40 hours for some metal parts. These all add up in terms of, they all hit on the energetic side. The reason I remember that this reminds me of this is that the key arguments that are made for additive manufacturing and the environment is that you have to look at sort of the total life cycle. And so we can go upstream from the build itself and look at the materials. And so, for example, we can use, I think maybe I'll talk about this in the next presentation. We can use materials like wood and stone, which have very low embedded energies. That is, it doesn't take much energy at all to produce it, compared to, say, titanium or one of the other metals that require a lot of energy to produce the feedstock. And so if we can take advantage of using low embedded energy feedstocks, then that helps with the environmental effects. Perhaps more significant is on the downstream side of additive manufacturing, where what we can do is you imagine that if I can take a part and I can build it in additive, again, say by topology optimization, so that it weighs less. If I put that on a vehicle like an automobile, or more importantly on an airplane, then what I can do is I get fuel economy. I get better mileage, as it were, by doing that. And so while it might be not very energy friendly in the additive manufacturing part of the stage, if we look at the energy savings in the service life of the part, that can be quite significant. And so this, I think, is probably the strongest argument that can be made for the environmental benefits of additive manufacturing. Yeah, it all came because of improved functional performance. Reminded me of this. Okay, so anyway, let's we can charge on here. This is another application of a that's I believe in the maritime. Yeah, this is a yacht application. So this is a they call it a cowl vent. You know, I've seen these in the movies where it's basically a structure like this that you see. I guess there's a hole down here. This bolts onto the deck someplace, and it's built in aluminum. Again, it's we can just tell from the context. You know, it's a fairly large part. Looks to be maybe a meter, 1.3 meters tall. Built in aluminum. I think this shows the actual construction phase, the build phase of the and with the DED equipment here in the background to produce the part. And again, they talk about the advantages: unique geometry, efficient production, cost efficiency, and on-site printing. I'm not sure why. I guess if they're doing on-site printing, I guess they move the machine to the location where it will be constructed. And certainly, I guess you can do that if there's an advantage to doing so. Okay, this is a rocket thruster. Again, wire arc added and manufactured. 308 stainless steel, about 0.2 to 0.4 meters in dimension, with 4 millimeter wall thickness. 9 kilograms of material in the part, and a print time of 10 hours. So again, this is we're building a part that's half a meter tall in 10 hours. That's not bad. And I don't know if this thing would be finished at all, but we can see that it has enough geometry that would make us think that additive would be a good way to go. And because of the size and the desire to build quickly, using great energy deposition over the other approaches makes sense. Here's a case, this is a mission, I'm not sure what a mission optical bench is. This is one of the cases I found where plasma arc directed energy deposition is used. The material is titanium, and we can see that it's a quite large structure, and there's enough geometrical interest in this to warrant using an additive manufacturing process. And the size certainly, again, makes us think that directed energy deposition would be the way to go. I like this application. This was one of my favorites. It's basically in Japan, Tanaka steel connector. It's a wire arc additive. It's a steel. I guess this is supposed to be a hollow core filled with water. So they build this structure. You can see it here in place. It's basically a structural member for a building. And you can see there's various ones of these, all presumably with different shapes. And so it goes into service, and so they can basically fasten to it in a way that preserves, I guess, some kind of optimum design guideline for building construction. And so it's basically these connectors that we see. Finally, we have some examples of cold spray. I wanted to at least show one example where we're doing cold spray. And again, it sort of falls in the direct energy deposition category, except with cold spray, we're not heating the feedstock. Rather, we're using kinetic energy. We're accelerating the feedstock, typically powder form, and it's being accelerated onto to a substrate, and it splats and basically solid state welds, particle by particle, to create a part. And then again, if we go back and look at the DED companies that I had at the very beginning of this presentation, what we see is I've also listed the cold spray companies as well that do this. So one of the challenges with cold spray is being very discriminating with where the material goes, because it's just sort of blowing a beam of material onto a surface. But as we can see here, that there are ways to try and make that happen. So we can look at these. I mean, it shows, for example, the examples that they have on cold spray is putting coatings or surfaces on cookware where we might have maybe typically the multiple material cookware that I've seen is basically you have one material that is very strong and scratch resistant, and then you also have another material that's a high thermal conductor, so it can conduct the heat to get a uniform heating. And so that appears to be what's going on here, where we have what looks like aluminum or steel, this back maybe with some kind of copper-based alloy. There's an example, I guess, of a brake disc, again, maybe using cold spray, bus bars. And again, one of the features of cold spray is we can't use multiple materials, right? We turn off one jet, turn on the other one, and blast it down. Cold spray it's not an energy freebie because it takes quite a bit of energy to accelerate these particles to velocities that can result in solid state welding when they hit the substrate. And as you might imagine, there's some geometrical limitations on what can actually be produced. So, they show, just to jump down here, they show this engine crankcase. I'm not really sure how this is produced with cold spray, to be honest with you. But again, they have multiple materials, the sputtering target, this hybrid heat state, again, is a multiple material application. And it may be a add-on part, because to be honest with you, these substrates that appear to be sort of made out of aluminum or silver metal, they kind of look like extrusions to me, not additive parts. So it may be that they're just doing cold spray down the material on the surface, and perhaps in both of these cases. This shows a combustion chamber where we have again a bimetal part produced by cold spray. And I guess one of the factors with cold spray is you have to have a line of sight for the particles to travel. Right? They can't curve. So I'm assuming that this was designed in such a way that they can shoot the particles in this way to get this part of the inner chamber, and particles in this way to get this side of the chamber. Of course, for the ones here, they can simply shoot straight in. That's not a big issue. So anyway, so just show some examples of what can be done, with cold spray, which again, if it's as an additive manufacturing process, it's not really directed energy in the traditional sense, although the argument's made that the energy source here is kinetic energy from the acceleration process. So in that case, we can sort of at least make an argument that cold spray would fit within the directed energy deposition mode. It's certainly directed, it's certainly energy, and it's certainly positive. So we have that going for us. Okay, so with that, I think I'm at the end of the case studies that I found. Again, these are dealing with just general directed energy deposition. We'll be looking at repair and hybrid applications in the next lecture on Friday morning. So again, just to summarize, there's a large number of DED manufacturers. As a matter of fact, I think I may have mentioned, I was a little surprised there were so many, maybe 40 or 50 manufacturers of equipment in the world. Also, remember we talked about 3187, which I think is an excellent guide for all things DED. I think it's a great resource if you're actually doing the processing to be able to really do the process well. And again, in order of decreasing surface finish, decreasing surface finish, or increasing build rate, we go from a laser powdered infusion to laser powdered DED to a laser wire DED to hard DED, and then finally to electron DED. So at least in terms of process selection, based on those two criteria, this gives some rationale for which process one might select. And then finally, the case studies emphasize common features of DED parts, geometric complexity, low production numbers, and again, generally large parts, because that takes best advantage of the high deposition rate capabilities of DED that don't really exist with very many additive manufacturing processes. So with that, I think I'm at the end. So I think we're maybe about 15 minutes out. So I guess we can see if there are questions or anyone wants to talk about something related to this.
Do you need one, sir?
Yeah.
That would be better. Evening time.
It is about surface finish uptime any of these processes. Whatever many of the processes. What is the surface finish uptime out of these processes? Is there any finishing process or super finishing process like bar machining requires to take the product into the end use?
That's okay.
Asking any surface finish which is used
For specifically for DED?
Specifically, yes.
Yeah, that's an interesting question. I'm not aware of anything specific to DED. I mean, for the large parts, they all look like they're just regular standard machining, right, for finishing. At least that's what I see here. Is that of course can apply to any additive process for metals. I'm not aware of a specific finishing. The finishing processes that I've seen in metals is well, obviously machining is the most popular of the ones that I've seen. Of course, that doesn't mean it's the best, but there also are some very large finishing chambers that use abrasive grid or milling that the parts just get thrown in and they turn it on and it sort of skirts around parts. And you pull the part out and it has a reasonable polish. It has an advantage because depending on the size of the grid, you can polish in places where it's not very easy to get to. So. Yeah, there's some water here. Yeah, so anyway, that's, again, I think certainly by and large, I'm not aware of any specific finishing technique that works particularly well for DED. I guess, yeah, Yeah, but I'm sort of rattling through the different finishing techniques, and I don't think the other ones really aren't even apply to DED, because the parts are generally pretty large. You know, because you can do things like painting, you do things like electropolishing, and then, you know, I mean, obviously, you know, things like grid blasting can have a positive impact on the surface finish as well. And, you know, those are all, well, some are relatively straightforward and expensive processes, but none of them are specific to DED that I'm aware of. So.
You shown one spherical tank, case study. Spherical tank.
The spherical
tank.
Yeah,
You
sure.
showed,
Yeah. Oh, yeah.
Spherical tank.
Yeah, you want to see that? Yeah.
Are you using any support structures or how?
Yeah, for like some of these parts, you refer to like the spherical part particularly?
Yes.
Yeah, actually, I need your help over here, because I think I froze up your computer. Yeah, I was gonna go look at it, but, so, yeah, I was afraid to control that stuff. Oh. Yeah, I think the answer is, for that spherical part, I don't think they needed support structures. And the reason why is, even though they're building out, it turns out that with additive manufacturing, you can actually build overhanging structures without a support structure within limits. And so you're sort of building out on the edge of the previous layer, so you have that support. So we don't need an external support to do that. And I'm speculating that spherical part, that they were able to build the part in that way without having to do support structures. So I don't know if that answers your question, but I think that, you know, that they do not need support structures for that relatively simple geometry. And they're building it. Yeah, thank you very much. Yeah, you know, they're building this thing out in such a way that I think they're able to build with it onto the previous layer, rather than having to have the support structure. And it clearly was built this way because we see the base plate. So, yeah. So I think they were able to avoid it. So, yeah.
Any other queries? Okay. Yeah. If there are no queries, we'll end the session here. We'll be back tomorrow in the same room. Okay. Thank you.